Case study, enhancing cybersecurity with autoencoders, anomaly detection at SecureBank. Autoencoders have become a pivotal technology in the field of deep learning, particularly for detecting anomalies in cybersecurity. Consider a scenario involving a financial institution, SecureBank, which faces increasing cyber threats that put sensitive customer data at risk. To address this, the cybersecurity team at SecureBank, led by experts Dr. Emma Carter and her colleague, Mike Thompson, decides to implement an autoencoder-based anomaly detection system. The team's first task is to collect and pre-process a comprehensive dataset representing typical, non-malicious network behavior. They gather data from various sources, including network traffic logs, user activity sequences, and system process logs. Emma and Mike ensure the data is normalized and handle any missing values to create a robust dataset for training the autoencoder. Emma explains, pre-processing is crucial. Any anomalies in the training data can compromise the model's performance. How can we ensure our training data is free from anomalies? Emma and Mike design the autoencoder with an encoder that compresses the input data into a lower dimensional latent space and a decoder that reconstructs the original input. They choose mean squared error as the loss function to minimize reconstruction error during training. What architecture and hyperparameters should we select to avoid overfitting? Mike wonders. They decide to use dropout and regularization techniques to prevent the model from becoming too adept at reconstructing the training data, which could lead to reconstructing anomalies as well. With the autoencoder trained on the benign network traffic data, Emma and Mike deploy the model in a real-time environment. The system continuously monitors incoming data, calculates reconstruction errors, and flags anomalies based on predefined thresholds. One day, the system detects a significant spike in reconstruction errors, indicating a potential security breach. What could be causing this spike in errors? Emma asks, prompting the team to investigate further. The team discovers that an unauthorized intrusion attempt was made on the network. This is quickly flagged by the system due to the high reconstruction error. The autoencoder's ability to handle high-dimensional data allowed it to detect subtle deviations from normal patterns, making it well-suited for identifying such sophisticated attacks. How can we improve the interpretability of our model to better understand the nature of these anomalies? Mike raises another important point. They decide to integrate clustering techniques to provide more context and interpretability to the flagged anomalies. As the attacks become more sophisticated, Emma and Mike explore hybrid models that combine autoencoders with recurrent neural networks and long short-term memory networks. These models capture temporal dependencies in sequential data, enhancing the detection of time-dependent anomalies. For example, by analyzing user activity sequences over time, the model can identify unusual patterns that may indicate insider threats or fraudulent activity. How can we leverage hybrid models to detect more complex, time-dependent anomalies? Emma queries the team, driving further research and development. To quantitatively assess the effectiveness of their anomaly detection system, Emma and Mike use metrics such as precision, recall, and F1 score. Precision measures the proportion of correctly identified anomalies out of all identified anomalies, while recall measures the proportion of true anomalies that were correctly identified. The F1 score, as the harmonic mean of precision and recall, provides a balanced evaluation of model performance. What trade-offs should we consider between false positives and false negatives in our cybersecurity context? Mike asks. They recognize that both types of errors can have severe consequences and strive to find an optimal balance. The team also explores advanced architectures like variational autoencoders and generative adversarial networks for enhanced anomaly detection. VAEs introduce a probabilistic approach to the latent space representation, providing a more robust framework for handling uncertainties and variations in the data. GANs use a generator-discriminator framework where the generator creates realistic data samples, and the discriminator distinguishes between real and generated samples. This adversarial training process enhances the model's ability to identify subtle anomalies. How can VAEs and GANs improve our anomaly detection capabilities? Emma discusses with the team, leading to further experimentation and improvements. By continuously monitoring and refining their system, SecureBank ensures the robustness and effectiveness of their anomaly detection model. The integration of autoencoders with other machine learning techniques enhances their ability to identify and mitigate security threats. Emma and Mike conclude that while autoencoders offer significant advantages, careful consideration must be given to model training, data quality, and interpretability to ensure effective deployment. To summarize the lessons learned and solutions to the presented questions. 1. Ensuring training data quality. It is vital to pre-process data by normalizing and handling missing values to avoid training the model on anomalous data. Regular audits of the training dataset can help filter out any anomalies that might be present, ensuring the model learns only from benign behavior. 2. Preventing overfitting. Techniques such as dropout and regularization are essential to avoid the model becoming too adept at reconstructing normal data, which could lead to reconstructing anomalies. Careful selection of model architecture and hyperparameters, along with cross-validation, helps prevent overfitting. 3. Interpreting anomalies. Integrating clustering techniques or rule-based systems can provide more context and interpretability to flagged anomalies, helping security teams understand the nature of threats better. Visualizing the latent space representations can also aid in understanding the clustering of normal and anomalous data. 4. Leveraging hybrid models. Combining autoencoders with RNNs or LSTM networks helps capture temporal dependencies in sequential data, improving detection of time-dependent anomalies. Hybrid models enhance the ability to detect sophisticated attacks by leveraging the strengths of both architectures. 5. Balancing precision and recall. Understanding the trade-offs between false positives and false negatives is crucial in cybersecurity contexts. High precision reduces false positives, while high recall reduces false negatives. An optimal balance ensures that the model is effective without overwhelming security teams with false alerts or missing critical threats. 6. Exploring advanced architectures. VAEs and GANs offer robust frameworks for handling uncertainties and variations in data, enhancing the model's ability to detect subtle anomalies. Experimentation with these advanced architectures can lead to further improvements in anomaly detection capabilities. 7. Continuous monitoring and refinement. Regular updates to the model and training data ensure that the system adapts to evolving threats. Implementing feedback loops where flagged anomalies are reviewed and, if necessary, incorporated into the training data helps the model improve over time. The case of SecureBank highlights the importance of autoencoders in cybersecurity anomaly detection and provides valuable insights into practical implementation, challenges, and solutions. By addressing these key questions and continuously refining their approach, organizations can build robust defenses against ever-evolving cyber threats.